Okay, so now it's recording. Yeah. So good evening, everyone. I'm Arti Shankar Banerjee, currently coordinator of Celestic from BSMS 2020 batch, IISc Tirupati. And today we are moving forward to our second talk of Cosmic Voyages series. And we have with us Dr. Banibrata Mukhopadhyay from IISc Bangalore. Before he joined in IISc Bangalore, he was in Harvard University, and prior to that, he has spent his time in various institutes of India that includes SINP, SNBN, CBS, SNBN, CBS, PRL, IUCA, and many places abroad as well, like University of Palermo, Italy, University of Oulu, Finland, and much more. So currently, he is working on various aspects of physics that generally include physics, astrophysics, cosmology, general relativity, astroparticle physics, and their interface. And he has significant interest in astronomy, observational astronomy, as well as data analysis as well. So today he is going to deliver a talk on the applications of quantum mechanics as well as statistical physics in general of astronomy. So over to you, Dr. Banibrata.
Okay.
Just as a side note, if anyone wants to ask any kind of questions, they can interrupt Dr. Banibrata in between. And if they cannot unmute, they can put their questions in the chat box and we will read it to Dr. Banibrata in between the talk. So feel free to engage with the speaker. Thank you. Over to you, Dr. Banibrata.
Okay. Thanks for the introduction and thanks for the invitation. Pleasure to be here. Uh, Actually, I was suggesting when I was invited, I suggested three titles, and other two are related to say more of formal astrophysical topics, current trend, for example, detailed of type 1 supernovae anomaly and super Chandrasekhar white dwarf, then accretion physics, jet, what is the underlying mechanism, that kind of titles, along with this one. However, I was eventually asked to give a talk on this. So it is uncovering cosmos by quantum and statistical physics. Although it mentions quantum and statistical physics, eventually I'll show you in parallel, in addition, you require basic electromagnetic theory as well, and of course classical physics, classical mechanics and relativistic mechanics, at least special relativity in some occasions cannot be avoided. I'll try to put the talk in such a way that at least senior UG undergraduate students will be able to follow, at least in some extent. There is a primary goal. So many stuffs I'll be covering would appear to be extremely trivial for master students or beginning graduate students. I believe hardly there is any graduate students attending this talk, and in that case, it's perfectly all right. So I aim at uncovering important astrophysical or cosmological issues, and I'll show, although those are extremely important issues, but in several occasions, if your undergraduate foundation is good enough, and if of course you have good vision, thought process, you should be able to solve the problem. With some example, of course, the varieties of astronomical and cosmological issues. I cannot cover everything. When I say I cannot cover everything, that implies there are many such problems which actually can be captured by knowledge of basic physics, which we have learned in undergraduate days. I'll take as examples for very few, three actually. Let's see how I could proceed. So basic themes. So by astrophysics, people generally mean combination of astronomy and physics. Astronomy is basically a branch capturing sky, stars, primarily sky, and then entities in sky, stars, galaxies, and so on. And when you try to understand the underlying processes, which in several occasions, physical processes, physics comes. So astronomy and physics together gives astrophysics. Now, astrophysics, of course, will have two broad branches: observational astrophysics, theoretical astrophysics. Observational astrophysics often deal with data, and often the data basically are satellite data, satellites sent to the space when there is no disturbance, no absorption. Say for X-ray, satellite has to be sent to the space, and it captures light from the various objects, say neutron star surrounding, black hole surrounding. Those are emitting of an X-ray. And those data, if you have to understand appropriately, your knowledge of statistics has to be very important. And of course, statistics cannot be processed without mathematics. So statistics and mathematics both are very important to understand astrophysical data, which is related to observational astronomy. On the other hand, theory, when we try to understand various astrophysical processes are mostly involved with physics. So physics has to come in astrophysical theory. Of course, observation has physics, but astrophysical theory cannot be thought of without physics. And often when we try to understand theoretical physics, we require underlying mathematical physics, which is the basic building block to formulate the system, formulate the object, to model the system. So physics and mathematical physics rather, and physics, both are important. So several problems, as I started telling a few minutes back, lie at the heart of fundamental physics. For example, baryogenesis, which typically requires statistical mechanics and quantum mechanics. I'll give an example. White dwarf mass limit. White dwarf is a dead body of a class of stars having mass not more than 10 solar mass. When they lose nuclear fuel, they get converted to a star called white dwarf. To understand white dwarf, and it cannot have mass more than certain value. I'll also little bit capture that aspect, and you will be remarkably seeing that white dwarf mass limit is nothing but knowledge of second year to third year undergraduation. We need little bit quantum statistical mechanics, Fermi distribution function, and general properties of matter. And not necessarily always you require electromagnetic theory, but sometimes electromagnetic theory is required. That is modern white dwarf mass limit requires electromagnetic theory. I'll touch upon. Finally, black hole spin, which is slightly advanced, which requires mechanics, relativistic as well as non-relativistic, some rarity process, and again statistical physics. So I'll first try capturing these two. If time permits, I'll go for black hole spin. I'm warning, this is a little bit more involved, but I would show that involved in the sense I'll take several techniques which are again borrowed from undergraduate physics, but some knowledge or some notions, some information like black holes here, etc., which cannot be understood unless you know rigorous relativity, which need not necessarily be the undergraduate topic. I'll see how can I proceed. So first, baryogenesis. What baryogenesis is? First of all, this is one of the enigmatic problems of today's universe. We see observationally total number of baryon means protons, neutrons, you all have heard are baryons, and they're antiparticle like antiproton, basically antibaryon. So total baryon and total antibaryon are not same. There is no as such obvious reason why they will be asymmetrized as we see today, but they are. Tiny 10 to the power minus 10 times photon number density. This is number density of baryon, number density of antibaryon, this is number density of photon. Though tiny, but it is there. But we physicists will still like to know why. Physicists' aim is to know, ask why. We are not happy with what we see. Why even that tiny difference will be there? To understand that, I need one concept called Dirac equation. Dirac equation apparently looks like a little advanced topic, but I'll show you it is nothing but relativistic, nothing but E is equal to mc square. You have been hearing. I'll show you. Dirac equation eventually describes relativistic particles dynamics. More precisely, relativistic particle having spin half, like electron, proton. They are called typical class of particle called fermion. Their spin is half integral spin, more precisely half spin half. Those particles, basically baryons are those kind of particle, fermions. And those are described by Dirac equation. I'll tell you briefly what Dirac equation, how does it relate with E is equal to mc square. Then I need gravity. Relativistic classical gravity. I'll show a little bit involved, but I think it is not difficult to visualize, at least for this context, gravity effect. Although this is little involved, but I'll show. It is not difficult. If you know electromagnetic theory a little bit, this gravity effect is not difficult to understand. And statistical mechanics. Let's see. Dirac equation. You all know E is equal to mc square. By the way, how many of you have not heard in this audience E is equal to mc square? If any of you have not heard, please tell, unmute and tell I have not heard. So basically energy and mass equivalence is equal to mc square. I square both sides, okay? But special relativity tells mass is actually not constant. By motion, if system is moving with velocity v, mass changes. So there's a rest mass, and due to motion, mass changes. If I split this mc square or m square c to the power 4 into two parts, one is rest part of the mass, and there is a mass modification of the mass due to its velocity, motion, then it can be split into two parts. So this is again E is equal to mc square or square of the both sides, but in little different way. P is the momentum. This is the rest mass. This is constant. This is not constant. Now, I think many of you already have learned Schrodinger equation, which is wave equation, right? Where if H card C are 1, energy written as I del del T, momentum minus I nablag, which is grad. If I substitute this here, Schrodinger equation is E is equal to P square by 2m plus potential or this mc square. But here I start with E is equal to mc square, relativistic thing. So it is little different. Momentum is momentum square and into c square, rather P square by 2m. If I substitute, I get this equation. This is called Klein-Gordon equation. And that equation describes remarkably spin zero, scalar particles dynamics. Still not spin half, still not Dirac, scalar particle dynamics. But this equation has a problem. So again, I'm recalling. I start with E is equal to mc square. This is nothing but E is equal to mc square, just squaring both sides. In wave picture. Now this equation has a problem. Unlike Schrodinger equation, which is first order in time, second order in momentum, but first order in energy and first derivative of time. Here second derivative of time. And as a result, when you compute the probability density or probability of any entity, which could be negative. I cannot go in detail of that, but very trivially one can solve. This equation will give possibility of negative probability, but probability is absolute positive quantity. So this equation has some trouble. Dirac was first who was bothered by this, and he understood this double derivative of time is the culprit. Then he has understood one has to go for first derivative of time as Schrodinger equation, which does not have any such problem, negative probability. But Schrodinger equation, this is first, this is second, but here both are second. So then he realized we have to take kind of square root. So both will be first derivative. but operator cannot be taken square root. He found out an way. He'll construct an equation whose square is this. And that equation remarkably is the Dirac equation. Little compact notation, but you just think mu is 0 means del del t. Del del t is partial derivative with respect to time. That is nothing but this, but first derivative. This, when mu is 1, 2, 3, momentum, which is nothing but this, which is square, momentum square. Momentum is grad, right? So this is, if you take square of this equation, you eventually get this. If there is no magnetic field. Now, I consider magnetic field also, I have in mind spin half particle. If both I introduce, magnetic field is bringing this extra term. This is magnetic vector potential. If charge of the particle is 0, this vanishes. Magnetic field doesn't matter. Now, if I square this, in order to get this equation, which is related to E is equal to mc square, but with magnetic field, you get modified equation. This is modified equation describing spin 0 or scalar particle, scalar's wave nature, you can think. This is Coulomb potential. You all know Coulomb potential. This A is in compact form. Mu 0 means Coulomb, A0. And this is your magnetic vector potential. I think you already have learned your Griffiths type vector potential. However, you have extra term, spin effect. Why spin effect come? Now, basically, I am talking about square root of original equation, and I am considering a particle which has ab initio half spin, say electron, proton, and particle is interacting with the underlying magnetic field, which is B. As because magnetic field is, that's why this A is sitting. And if you take square of this equation, it does not exactly go into this, but it will have this plus term with A, which is magnetic vector potential. Exactly this is somehow cut. I couldn't manage. I don't know. Some erroneous thing happens. This is energy plus potential. This is momentum plus vector potential. That potential, Coulomb potential and vector potential appear. In addition to that, this is the first correction due to magnetic field to the scalar particles dynamics is equal to mc square's wave nature, wave counterpart. But also this is there because I am dealing with spin half particle, electron having spin half, proton spin half. So two effect comes, magnetic field and this. Of course, magnetic field alone would bring this. If magnetic field is 0, this will not come. If I go to non-relativistic limit, you see Schrodinger type, p square by 2m. But p is modified to p minus ea, which is due to magnetic field. And this is mc square, c is 1. So kinetic term, potential term, and then spin magnetic coupling is coming. So this is typical, I assume many of you have learned Zeeman term, Zeeman effect. See, positive negative energy, and due to spin term, sigma term, further split, Zeeman splitting. Well known. I have not said anything very special. Zeeman splitting is well known. So I have basically so far talked about Zeeman effect. Very basic principle, E is equal to mc square, starting from E is equal to mc square, I have ended up with Zeeman splitting. Now, gravitational field. You will say remarkable analogy. Remarkable analogy. This is electromagnetic. IEA, I showed. Gravity has replacement of IEA by some quantity which is related to gravitational field. Here magnetic field or potential, here gravitational potential. It is a little complicated. By symbolically, it is as simple as minus IEA replaced by some quantity capital gamma. This is involved with this matrix. Remember, this matrix is Dirac introduced such that this its square has some interesting relation. Squares will have to be unity or minus unity, such that when you square, there is no such gamma, right? There will be unity or minus unity, unity or minus unity. So there is called Dirac matrix. So here, these terms will have background gravitational field like A and Dirac matrix. Similarly, if I write down the Hamiltonian, which is I del del t, you get little complicated term, but don't be too much. I mean, don't think it's too complicated. You just think right hand side, like here you had all these A term, momentum, magnetic potential, magnetic field, and so on. Here, right hand side, this capital gamma are basically coming from here, which is gravitational counterpart of magnetic vector potential. So gravitational potential. If I little bit do algebra, that clean up, you see it is the simple form. And further simple form. Like if I side by side cleaned picture, cleaned energy, I compare electromagnetic and gravity. Very similar picture. Here you have sigma dot B, here sigma dot momentum. Here pure scalar, here also scalar, but sigma is coupled with magnetic potential. This is not magnetic field, by the way, magnetic potential. Magnetic, it is A versus B. In that way, I am like A is vector gravitational. Sorry, it is gravitational potential. A is gravitational magnetic potential. B is gravitational potential. BG, not magnetic field B. This B is different than BG. Notice that may be slightly confusing. That's the way people do. Even my papers also do. So see, remarkable analogy with p square by 2m, Schrodinger's part, non-relativistic limit, and extra spin-based term. Sigma is involved, that means spin. Here also spin-based term, electromagnetic. Very remarkable analogy. So as you have Zeeman effect here, similarly gravitational Zeeman effect should be there. Which is this? So what?
Sir,
Yeah.
what is dA and d mu in that slide? The
P is
previous.
the momentum, particles momentum. P.
No, d.
Which D?
The
Yeah.
previous slide. The one, yeah, this one.
As
EMK
I
is
said,
d.
no, this D is for electromagnetic. This D is del minus IEA. Like this is D, total derivative.
Okay, I got it.
And for gravity, it is similarly, but in place of IEA, I have some capital gamma.
Okay.
Huh? So these were total derivative. You can think total derivative. So fantastic analogy. So I have also Zeeman splitting. Now important point which will be required for gravitogenesis is that for positive energy also I have splitting, negative energy also have splitting. So I can argue in terms of gravitational field, spin up particle and spin down particle are split like Zeeman effect does. Zeeman effect does that sigma dot B. What Zeeman effect does, sigma is carrying spin information. When spin carries couples with magnetic field, spin up has B magnitude B and spin down has minus magnitude B with half factor. So split. Here also for gravity also this as well as this together spin effect comes and splitting comes. So spin up has up energy, spin down has down energy, split. So now interesting point. So this I think so far no problem. If you know Zeeman effect, similar gravitational Zeeman effect comes. I hope it is understood at least. Now comes to the baryogenesis. Baryogenesis, which is baryon's asymmetry, I'll attack through leptogenesis. I'll show there is some conservation lepton baryon number difference. And lepton means like baryons are protons, neutrons, and so on. Leptons are electrons, muons, tau, neutrinos, and I capture neutrino. Those are leptons. Electrons like electron, neutrons are lepton. Difference is electrons have mass, neutrino ideally does not have mass. But these days people talk about massive neutrino, otherwise certain phenomena cannot be explained, like neutrino oscillation, solar neutrino detection. Neutrino has tiny mass but very small mass. According to standard model, 1979 Nobel Prize, neutrino does not have any mass. Now, I'll first attempt to understand leptogenesis. Then I'll go to the baryogenesis. And neutrinos are lepton and how to get leptogenesis. I already argue this is spin-up particles. Gravitational Zeeman is coming, giving spin-up particles split. Why spin-up? Because this two Pauli, this sigma is carrying information spin. Only spin half particle will give this splitting. Now, upspin and downspin of a particle have split of energy, you understand. Now, according to standard model, Weinberg-Salem, Glasgow standard model, electric model, I'll not confuse you. Neutrinos are purely upspin, antineutrinos are purely downspin. That means for neutrino, only one component which is upspin. So particle having upspin, which is by definition neutrino, particle. And particle which has downspin by definition antineutrino, which is antiparticle. So for neutrino sector, split means split between particle and antiparticle. Particle is lepton, antiparticle is antilepton. For neutrino, this is gone. For antineutrino, that is gone. For neutrino, this is gone. Antineutrino, that is gone. So for neutrino, this survives. For antineutrino, that survives. So now, very simple statistical mechanics. We know Fermi distribution function. And if you are given Fermi distribution function, because they are all fermion particle, spin half particles, half integral spin particle. If you are given fermions, you know how to obtain number density. This is the formula. Number density is basically distribution function and volume. And then, of course, you have to take care of minimum number of volume, minimum volume, which is related to H card and so on. For neutrino, this is the number density, and for antineutrino, that is the number density. Because this is E nu, this is E nu bar. And neutrinos and antineutrinos are split in energy. And if you take, as because E nu and U nu are different, this number density will be non-zero. Unlike conventional case, neutrino and antineutrino have same energy. But here, due to splitting, due to gravity coupling, due to this term, up and down spin are split. And up is neutrino, down spin is antineutrino. Up is lepton and down is antilepton. You get energy difference, you get number density difference. If you do algebra, remarkably it turns out that number density difference by photon number density is gravitational coupling potential by time. If you substitute the value appropriately, we know where it is generated, temperature, at that system, what is the gravitational coupling. I am not going to detail. I will try to capture some other interesting application. If you substitute, I'm just basically giving basic idea how fundamental physics is important. So just statistical mechanics and electromagnetism I have taken so far, nothing else. And is equal to mc square. If I substitute all the value, you will get actually the number, what I quoted at the beginning, 10 to the minus 10 will be obtained. Now, so far I talked about only lepton number violation.
Sir, the part where you explained like antineutron and neutron would have the
antineutrino, not neutron. Antineutrino and neutrino. Neutrons are baryons. Baryons are lepton. I'm talking about only lepton.
Yeah, so in lepton's case, both because of splitting, they will have like different energies. You say that?
Yes, leptons have lepton upspin, lepton downspin have different energy, but here lepton's upspin itself is lepton and downspin itself antilepton.
Okay.
Because I'm talking about neutrino. Neutrino has no downspin, antineutrino does not have any upspin, ideally.
Okay.
And so this is neutrino counter, but this is neutrino contribution, this is antineutrino contribution. Difference is number density difference. Now, there's a process called Phaleron process, which argues B minus L is conserved quantum number. That is, whenever you have standard model particle, basically, say, don't get confused by standard model, conventional particle, which are interacting with magnetic field. So electroweak interaction is there. Some anomaly is there, which argues for non-conservation of baryon number, which argues B minus L is conserved, not B and L separately, but difference is conserved. So if L is violated, which is coming from delta N violation, delta N is shown to be violated by neutrino asymmetry, equal B will be violated, B is baryon number. So that way, delta L creates delta B, baryogenesis. And you can show that, I'll not go in detail. There are time of the universe evolution, or today's black hole, today's universe, when there are black holes are sitting here and there, also has gravity around it, strong gravity. Temperature and gravity effect are such that what we observed 10 to the minus 10 could have been predicted by this. So I use E is equal to mc square. I use electromagnetic theory. I use simple quantum statistical mechanics to just, we're not high standard, just number density calculation with Fermi distribution function. That should be able to solve baryogenesis. If you just little bit extrapolate, that you have to borrow some idea of gravitational coupling as opposed to magnetic coupling. That you have to borrow. Now, there are many bounds where from you can, so we have to assure that this B, what I am talking about, this B, not this B, I am talking about this BG, should be visualized in our Earth-based experiment. So this is a gravitational coupling. So why we require black hole? What is the B value, gravitational coupling in Earth? We can show that. Suppose we consider, I'll not go in detail, but let's consider a satellite. Let's consider a satellite around Earth. And satellite has some neutrino. So Earth gravity is affecting the neutrino. Then Earth gravity is so tiny, effect turns out to be 10 to the minus 37 GeV, that B. And as a result, asymmetry will be very tiny, which is unnoticed, not noticeable. That is why in Earth, in principle, also leptogenesis is there and baryogenesis is there, but this practically is zero because B effect is very small. But in gravity, in black hole or very early universe, gravitational power is much stronger than Earth. This 10 to the minus 37, what is in Earth, would be much large, and you have adequate asymmetry, what you observe. Others I am not going to detail. Next is white dwarf. White dwarf mass limit could be understood again by very basic physics. In a celebrated paper, Subramaniam Chandrasekhar, Indian American Nobel laureate, showed that maximum mass of a non-magnetic, non-rotating white dwarf is 1.4 solar mass. Such star is governed when normal star, conventional star of mass 10 solar mass or less have stopped their nuclear burning. Then a situation form such that gravity is balanced by degenerate electrons. What degenerate electrons are, I'll tell you. And you arrive at when this balance comes, degenerate electrons balance by the gravity, limiting mass comes. Basically, that's not only limiting, that's a white dwarf phase, and then that mass cannot be beyond certain value. I'll show you how. What is degenerate electron? First, I have to understand. Again, quantum statistical mechanics is important. We know Fermi distribution function is associated with some quantity called Fermi level, particularly when temperature is small. So, and fermions also obey Pauli's exclusion principle, that such that suppose levels are there, 1, 2, 3, 4, 5, 6, levels are there. You are putting fermions in the box. Each level is unique, such that each level is unique for a particular particle. No two particles can be occupied by same level. That each level is assigned to a particle's quantum state. So you have one particle, next particle I have to have a second level. So that way they are separated. Now star is losing nuclear fuel, gravity is winning. Okay, as it was nuclear fuel which was producing radiation and outward pressure, that was balancing gravity. Now nuclear burning stops. As a result, star collapses. There is nothing to oppose gravity. Star collapses. As star collapses, by simple statistical mechanism, one can show density of the star collapses means density increases. Density is related to Fermi energy. Larger the density, larger the Fermi energy. But so density and Fermi energy are related. In a given density, fixed Fermi energy is there. So in a given density, fixed number of electrons could be there. And why electrons? Because one can show that when all nuclear burning is, or not all, momentarily nuclear burning is stopped, lot of new electrons are produced. You can simply think, right, that neutron decays to proton, giving electron, right, beta decay. So electrons are populated. Electrons are fermions, obeying Pauli's exclusion principle. And density increases. Density is related to EF. So now maximum, the level of electrons which are distinct, and electrons are occupying first level, second level, third level, so on, EF, maximum level. Now, there is a situation, all levels are filled. There is no space to fill in further electron. And not only the electrons, you further contract, star is collapsing due to gravity. Gravity is winning over outward pressure. Star is collapsing. So electrons are coming very close. Levels are coming very close. They are opposing. Electrons cannot be coming close together because they are obeying Pauli's exclusion principle. Two levels cannot be merged. They are opposing. And that opposition among electrons are effectively producing outward pressure. And that at some point balances the gravity. And that is the white dwarf phase. I'll show why that has also limiting mass. So that exactly I have mentioned in these few lines. So Pauli's exclusion principle is very important, which is basic quantum mechanics, and quantum statistical mechanics tells that fermions cannot have, two fermions cannot have, two different fermions cannot have same level. Together, extra pressure comes. When they are overlapping, they are hitting each other, they are opposing each other, and that they are hitting each other, countering each other, is producing effective pressure that balances gravity. So basically, difference between fermions and bosons. For fermions, positions are distinguished. For boson, particle 1 and particle 2 can be either position 1 and position 2. Either way, particle 1 can be position 1, particle 2 can be also in position B. Particle 1 could be at position A, particle 2 also could be, particle 1, if at the beginning is in position A and particle 2 is position B, you can also say if it is, they are changing position. Particle 1 is in B and 2 is in A, there is no change of the system. But for fermions, there is a boson initially. For fermions, if A, B are interchanged, or 1 or 2 are interchanged their position between A and B, then negative sign comes, and that changes the wave function. So they are not, basically system is now changed. Wave function changes, system changes. So they are not allowed to shock. Now, when you have strong magnetic field, so basically Subramaniam Chandrasekhar showed this is a pressure density relation. This. When you have strong magnetic field, what happens? If field is in vertical direction, say this picture, perpendicular direction also have quantized energy. I'm not going to detail. That gives extra effect. So strong magnetic field gives larger pressure for a given density. Here Chandra, without magnetic field, with magnetic field for a given density, you have larger pressure. And see exponent, 4/3 versus 2. I'll now show first Chandra's result, then modification of result, modifying result with magnetic field. This is just nothing but general properties of matter. I'll show you. This is basically the gravity balanced by outward gas pressure, and that gas is electron regenerate gas, as I explained you. System is full of electron and they are opposing and giving pressure. This is in a given shell mass, dm in a cell dr, nothing but that, assuming spherical star, spherical white dwarf. Now, if you solve this equation, or if you combine these two equations, you get this little different form, and it can be shown as I showed here. At high density, P is equal to rho to the power 4/3, and there's a relation between gamma and n. I'll tell you why n is important. Basically, this is a relation. If gamma is equal to 4/3, n could be 3. If I write equation state in terms of n rather gamma, that is useful often. That's different language. You can show mass by simple algebra from general properties of matter. Mass proportional to central density to the power 3 minus n by 2n. And extreme high density tells n has to be 3. Gamma 4/3. Gamma 4/3 means n3. n3 means mass is independent of density. So beyond certain density, mass doesn't change. Independent of density. And that exactly you see Chandrasekhar had calculated radius and mass. Each and every point is a mass. Each and every point is a star, white dwarf. Initially, with the change of density, mass increases, radius decreases. Beyond certain density, n becomes 3, gamma becomes 4/3. You see, mass saturates 1.44 solar mass. That is famous Chandrasekhar limit. Just by simple algebra, you can see this is the key point. M proportional to rho c to the power 3 minus n by 2n, and that power becomes 0 at high density. By simple algebra, one can show. But remarkably, this proportionality constant, etc., when you substitute, mass turns out to be, all that is macroscopic phenomena. Star is a macroscopic body. Final result, this limiting mass, is in terms of fundamental constant, Planck's constant, speed of light, Newton's gravitation constant, and so on. If I substitute everything, it is 1.4 solar mass, 1.44 solar mass. That is famous Chandrasekhar limit. So by solving these two equations, and quantum statistical mechanics assures this form. Simply. Now, when you have magnetic field, momentum balance is modified. General properties of matter is still valid, but magnetic field is included. And this rho c power is there, but k, some proportionality constant, is no more pure constant. This proportionality constant is also a function of rho c. If I combine, proportionality constant is function of magnetic field and rho c. If I combine, it turns out that effective power of rho c is looking like 1 minus n, like here. And magnetic field has 1 minus n, and without magnetic field actually has 3 minus n. So extreme case like here, n1 means gamma 2. This is the extreme density situation. For magnetic field, we substitute, this is a limiting mass. Like this, you get from this algebra. You get this. Same I am borrowing in this slide. But when k is not constant, when you have magnetic field. Non-magnetic k is constant, same result as I had in previous slide. With magnetic field, effectively this is the result. Scaling law. Sorry, this is radius.
Sir?
I'm sorry, this is radius. If I combine this, just a minute.
Hello?
This is a scaling law. Just a minute. This is the scaling law. But it will be 1 minus n. I'm sorry, this is not the correct. This is the radius law, but this is the mass law. Rho c will come from here, and if you combine, 1 minus n will come. And if n is equal to 1, extreme case, again mass is there in terms of fundamental constant. But in terms of 1.44, here it is 2.58. Magnetic field enhances the Chandrasekhar limit. Yeah, go ahead.
Yeah, so in Chandrasekhar limit talks about like non-rotating white dwarfs, right?
Yes, original.
So originally. So when we are talking about the magnetic fields, we know that the rotation of the stars on their own axis also produces magnetic field. So are we talking about that magnetic field
No.
or some external one?
Basically, already magnetic field is produced from the original star. That it is being carried from the original star. Initially, it might be due to motion of charged particle, and that could be self-generated field. But this here I am talking about something called, it's called fossil field. Original star field is leading to large field, something called conservation of magnetic flux. Larger radius has small field, smaller radius has large field. And that small field is becoming large field when star is small. White dwarf is smaller than normal star. That field could be large. But
Okay,
what
sir.
you are saying, that also could be in addition playing role. But as you said, here I am not considering rotation, so that effect will not be there.
Okay, sir.
So side by side, if I show you here, Chandra, and this is our modified mass radius relation, about 2 point, actually depending on the, not only here, ideally, when there is no Lorentz force, 2.6 solar mass, but when there are Lorentz force in addition and some extra effect, it is 2.8 solar mass. At Chandra is 1.4. And theoretically also you see two different mass values. Both are in terms of fundamental constant, but limiting mass. This is magnetized limiting mass, this is non-magnetized limiting mass. What is the immediate implication? There are several, okay, white dwarf is one of the important implications of white dwarf is to understand the size of the universe. When white dwarf is exploded, when it reaches the limiting mass, whether Chandrasekhar's limiting mass or other limiting mass, when it reaches the limiting mass, it explodes because it becomes very hot. Gravity cannot be balanced by any outward force. It collapses. All leftover nuclear fuel is burnt out and produces a huge energy that we see as type 1a supernova. Type 1a supernova is always at fixed burning mass, which is limiting mass, considered to be standard candle. What is standard candle? In the sky, when there is type 1 supernova, luminosity is fixed because it's coming from the limiting mass, which is known theoretically. But we see with time that luminosity, what we see in the sky, keeps, basically flux keeps changing. Luminosity is fixed, fundamental quantity, but flux keeps changing. Flux changing means distance changes. Distance changes means universe size changes. That's why type 1 supernova plays very important role, as it has fixed luminosity to understand the size of the universe and expansion history of the universe. But generally, their luminosity with some error bar observationally lie in a narrow zone. But there are some type 1 supernovae are having extremely high luminosity, which cannot be explained by conventional cases, such that they are arguing to have progenitor mass, which is exploding to giving that high luminosity is 2.8 solar mass by this Nature paper by Andy Howell. And that peculiar type of supernovae could be explained, that magnetic white dwarf, what I just now explained. And if this is there, there are, of course, at least 14 such peculiar, but still 14 is very small number compared to astrophysical objects, vast astrophysical objects. But eventually many such objects are discovered that severely questions about considering type 1 supernovae to be standard candle. Because by mistake, if you choose one type 1 supernova to be exploded as Chandrasekhar mass limit and calculate luminosity, and based on the luminosity and calculate flux and calculate expansion history, you are getting wrong result. One has to be very careful. So if many peculiar type 1 supernova high luminosity comes, it threatens expansion history and dark energy idea. But right now, I think what calculation people have, as because this strange objects called peculiar type 1 supernovae, not many, not populous, I think okay. But future one has to be very careful. Now, last 10 minutes. By the way, my speaking time is 1 hour, or with question answer 1 hour?
Sir, it's all right. You can take 10 more minutes and then we can have few questions at the end.
Okay. My last part is black hole spin. So this is slightly more involved. I require some general relativity, but I'll explain whatever I require. I'll at least flash. Black hole spin. So effectively, it is not quantum nature of the black hole. Quantum spin, classical. Angular momentum per unit mass of the black hole. Like cricket, off spin, leg spin, clockwise, counterclockwise. Similarly, black hole can have a clockwise or counterclockwise spin. Like when you bat, by looking at the ball, you understand prior to you hit the ball. I don't know how many of you are cricket freak. I am. But at your age, I used to play a lot. I only used to play. I would not do any science. And just looking at the grip and also as well as the ball, basically one is to anticipate. It will be off spin, clockwise, and anti-clockwise. Because ball has a surface. From the surface, you get the light. But black hole has no surface. If black hole doesn't have any surface, who will emit? It's the black. So black hole spin measurement is extremely difficult. Theoretically, Roy Kerr showed spin could be varying between 0 to plus minus gm by c. G is Newton's constant, m is mass of the black hole, c is the speed of light. Theoretically, if mass of the black hole is known, spin corresponds to a radius in the space-time around the black hole, where time dilation becomes infinite. Means if I speak sitting next to you, you never will hear my voice. It will take infinite time to reach infinite time dilation at pole. Or another language, if you don't want to go to the pole, it is a position when particle cannot be static, called static limit. And that former, when time dilation is infinite at pole, is also black hole radius, called black hole event horizon. So, as I said, measuring spin is difficult due to absence of hard surface. It gives a taste of general relativity, particularly general relativity of rotating solution of the Einstein equation. One has to rely upon environment of the black hole. Because black hole cannot be probed. One has to only look at the environment, which is giving light, unlike black hole. What is the environment? Accretion disk. Black hole is eating matter, and due to matter energy, matter angular momentum, matter does not fall radially. It falls, forming a disk-like structure called accretion disk. Powerful jet also form. In case of complete fall, some of the matter is kicked out by jet. So disk, jet together, inflow, outflow, both are there. Those are the environment of the black hole. This is a typical way of understanding, again, high school physics, radial direction, azimuthal direction, and it will fall through diagonal, right? We knew. And like running through rain. Rain hits you through diagonal. Same physics, but diagonal goes to diagonal, eventually forms a disk-like structure and black hole. Now, quickly, special relativity. People, some of you know special relativity. It is not difficult to understand. Special relativity tells if particle velocity is approaching speed of light, time dilation is infinite. This is proper time difference, proper time interval. This is time interval, as you see, for moving particle, moving body. That motion is speed is close to speed of light. This diverges. Similarly, general relativity, when general relativity tells that, gravitational relativity tells that unit vectors which were constant here they are no longer constant, they are varying. Due to variation, this c square -1 which were unity will no longer unity. They are function of space, in principle time also. If I recast similar way as you did here in gravitational physics, you get again dt time interval in terms of proper time interval by something. Now f1, f2 as opposed to 1 -1 constant, here f1, f2, f3 are non-constant. If you had a fixed x, y, z, fixed position, then dx, dy, dz all are vanished. You simply have dt f1 to the power -12 d tau. When f1 is 0, that gives dt divergent. That means time dilation is infinite. And for rotating black hole, I'm not going to detail. This is if f1 is 0 at pole, you can get the size of the black hole. M is the mass of the black hole. A is the angular momentum of the black hole. What I said, gm by c, maximum gm by c, angular momentum of the black hole, classical angular momentum. Let's see how we proceed. So we have learned for black hole also, like special relativity, there is a radius. As opposed to v approaches c, here also at radius, time dilation will be divergent, large time dilation, and that point that point corresponds to black hole radius. Now, simple central force field, you will be remarkably knowing. For central force field, what is? Particle is sent from infinity coming to the gravitational potential, Newton's law, right? What you have? That gravitational potential, then particle is moving, not necessarily radial, centrifugal effect is there. This together is giving together forming central force field, right? And if you have added rest mass per unit mass, c square is there. So this is central force field, right? Nothing surprise. When you have black hole, I'll not go into the detail of the derivation, but for black hole, you have to trust me, extra term comes. This term only comes due to black hole. Central force field, but modified central force field. So original central force field has this effective potential. For black hole, in place of going up, continuously up, in place of Newton's law, going up, here for black hole, it goes down beyond certain radius. Because this extra term with minus sign, Here, this is positive, this is negative. This positive was taking over negative, close to r is equal to 0. But here, further negative takes over to over 1 by r square, because 1 by r cube, close to the origin, r is equal to 0. So it goes down. So there is a radius, turns out, which is r is equal to 2g by c square for non-rotating black holes in special case when Vr is 0. And more importantly, as opposed to one minimum, here two extrema, minimum and maximum. They are playing a remarkable role to control black hole dynamics and particularly accretion disk dynamics. Black hole environment, basically black hole environment, is influenced by this extra term that I'll use for understanding black hole spin observationally. Next 3.5
Sir?
minutes. Yes.
Sir, yeah, there is one question over here that as we see black hole, why it's form in slowly spiral form? Why didn't directly take the whole mass once?
I don't get.
As we see black hole, why it's form in slowly in spiral form? Why didn't directly take whole mass once?
As I said, no. It could be possible if initial mass does not have an angular momentum. If, like here, if this phi component is not there, it will fall straight. But initial star, say star, which is supplying mass, star is presumably rotating. So when it is rotating and detached, mass is detached due to rotation, in place of falling straight, it will fall in a spiral, but like in swing. If it is straight ball, it will go straight to the batsman. But if you put in swing or out swing, it will be going like this, going like that. Swing. Similarly, it has initial angular momentum. So it is falling through this diagonal as opposed to falling radial, and diagonal is giving the spiral path.
Sir, one question I have, that the extra term that we are talking about in this case, does it mean anything like physically?
You are the organizer, that Arjit.
Yes, sir.
Okay, yeah. Extra term, what you are saying?
So the extra term that we are talking about over here, does it mean anything physically?
Yes. That basically coupling between these two terms, you can see.
Okay, so like in general cases, in Newtonian cases, we don't see two extremums. So like what special is happening in this here?
Because here, in general relativity, you cannot separate out gravitational potential, centrifugal potential, other potential. They're jumbled up because this axis, here axis are straightened, here axis are coupled, bent, so axis are straightened. So whenever you are trying to understand something, they are moving in curvilinear coordinate. As a result, entities are coupled. So you have pure entity and there's a coupling term. So coupling is basically gravity, gravitational potential, centrifugal potential coupled. So 1 by r cube comes. And so it is basically coming from the effective potential. I think easy way of understanding is the coupling between these two terms.
So since that is falling towards
You are
zero,
giving
like,
the extra minutes, right, Arjit? Because
yes, sir. Yes, sir. Yes, sir. Okay, perhaps I can ask it later on.
Maybe after I finish, you can
Yes,
ask.
sir, yes.
Because
Sure,
this is
sir.
straightforward calculation from the Lagrangian classical
Yes,
mechanics.
sir. Yes, sir. Sure.
And best physical way of understanding is they are not free term. All the energies are coupled because axes are not independent. Axes are jumbled up. Axes are jumbled up. There is no unit vectors are changing.
Okay, sir.
So now, observationally, from accretion disk, black hole does not emit, accretion disk emits. If I look at the emission of accretion disk, we find this kind of photon count as a function of time. Sometimes it's very jittering, sometimes has very good, gap, very well resolved, sometimes very jittering. If I go to the corresponding Fourier space, this is a time domain. If you go to the frequency domain, you often find a fantastic peak, sometimes double peak. Those peaks, people argue, are influenced by black hole spin. Those peaks called quasi-periodic oscillation. Why not periodic? Quasi-periodic. Periodic will have delta function. One particular point will have peak, start peak. Quasi-periodic means few other frequencies will have slightly moderate role to produce special effect. That's why little low amplitude but some broadened peak. So those will be probing by model, and model will have black hole spin for the best fit by observed data, best fit by a model to the observed data. Will be capturing the black hole spin. That's the idea. So here, observational knowledge, which is lying with statistical theory. Statistics is involved. Classical physics is involved. General relativity is involved. And yeah, at least these three are involved. That's why it is little involved part. Also, Fourier transformation, mathematical methods are involved. So idea is that matter is falling, and while falling due to various perturbation radially as well vertically, it is oscillating like this and this. Perturbation is there due to black hole's rotation, or it could be neutron star also, other object also. They are rotating. Their magnetic field lines are there. When magnetic field lines are there, it is rotating here, and field lines are connected here and there. So when it is rotating, it is shearing the environment. So environment is disturbed. So black hole's effect is imprinted in the environment through the field lines. One of the hypotheses. And environment means mass. So mass, due to all the disturbance, could be moving vertically, could be radially. So effectively, they behave like a oscillator system, and they can be explained by simple recasting coupled, forced, damped oscillator, which is the first year undergraduation or maybe second year. First year, maybe there is no coupling or maybe no forcing. I teach actually first year last time when I taught. I will be discuss forced damped oscillator, but they're not coupled. So motion around black hole, if you consider this perturbation due to various effect, are nothing but coupled, forced, damped. This is a damping term. This is the acceleration term, forcing term, and this is the oscillatory term. But radial, vertical, azimuthal are coupled, starting from original equation. Nothing. Now we have to just obtain the resonance, like we did in our undergraduate days. We have to get the maximum amplitude where and corresponding frequency of resonance, maximum power. That I do, get the corresponding frequency which is giving maximization amplitude. Those are the fundamental frequencies are basically here, and they are also having relation fundamental frequencies with black hole spin. When you have particles, black hole spin is influencing the environment, as I said, and their relation tells that this is the higher frequency, the lower frequency, and their relation is basically m black hole spin by 2. And that separation, m is playing role of separation, and that gives the separation. As I don't have time, just I am telling by simple coupled, forced, damped harmonic oscillator coming from the simple accretion physics, environment, matter motion around environment. If I little bit recast equation, it will recast into coupled, forced, damped harmonic oscillator. If I obtain the resonance condition giving maximum amplitude, that is why we are seeing QPO at that maximum amplitude. Corresponding frequencies are this. When frequencies upper and low are related by this law, which corresponds to resonance, and basically resonance is that. So this is the resonance concept. Two wave fundamental frequencies are matching. I'm not going to detail, as I don't have time, people will be bored. I would like to rather take question. But bottom line is that, as I said, spin, how to measure spin? I am probing by my model this observed data, this observation, observed data I am probing by my model. If my model is good, I should be able to explain these peaks. And my model parameters are black hole mass, black hole spin. Which black hole mass spin combination giving observational data perfect match? That mass and spin are my black hole mass and spin. And that exactly I tabulate. Various black hole sources I am tabulating. All have accretion disk. Light is coming from accretion disk that I analyze, and that light I am analyzing by my model, coupled forced damped harmonic oscillator. For best reproduction of observation, I get the black hole spin, which is there. 0.91 for this black hole. This is a very remarkably fast spinning black hole. Could be all the way 0.99 if I go to the upper error bar. Some black holes have low spin. It could be 0.65. As I said, 0.65 means 0.65 gm by c. Unit is gm by c. It is minus gm by c to plus gm by c. Gm by c unity means 0.65 and so on. So black hole spin can be obtained by simple knowledge of undergraduate forced damped harmonic oscillator. I'll summarize. Many fundamental astrophysical questions I believe I could convey you that can be uncovered by very basic physics, often knowledge gathered in undergraduate days only. I hope that I could convey. Mass limit of white dwarf is a big example, which is nothing more than general properties of matter and little bit quantum statistical mechanics in BSc class, undergraduate class. Also, a bit advanced quantum mechanics with some flavor of gravitational physics is adequate for baryogenesis, baryon asymmetry we see today in the universe. Mechanics and basic relativity could also enlighten the fundamental properties of black holes. By fundamental property, often fundamental properties of black hole is called black holes here. Here is symbolic of knowledge, spin and mass, which are astrophysically important black hole here. Spin measurement for observed data gives a natural test of Einstein's relativity for rotating black hole. That could be done. Understanding and analyzing astrophysical data is involved with knowledge of basic statistics and mathematics. I would say young students like you, maybe a bit senior undergraduate student, should come forward joining the astronomy group and solving puzzles. Thank you.
Okay, thanks a lot, sir. So, if anybody have any kind of questions, they can unmute and ask directly. Something we have in the chat box that, sir, can we get the notes of the slides?
Yeah. Sorry, you were
Will,
telling.
sir, someone has asked that if you can share the slides.
Oh, yeah, I can share. It's okay.
Okay, yeah, thank you, sir. So we'll be sharing the slides.
But you are recording the talk, right?
Yes, sir. Yes, sir. Yeah, the talk will be uploaded in our YouTube channel. So I will send the link in the chat box. Just a second. Yeah. Meanwhile, if anyone has any kind of questions, they can unmute and ask.
Hello, am I audible?
Yes.
First of all, sir, thank you. Great talk. Can you explain a bit more about the infinite time dilation? That part
Yeah.
is very interesting.
Yeah. Basically, you can see my slide, right? I'm now out of the slide so
Yes,
mode,
sir.
but you can still see, right?
Yes, sir.
Yeah. So basically, this part is special relativity. I hope you understand Minkowski four-dimensional space.
Yes, special relativity, general.
In general relativity, this -1, which is the constant, -1 constant, c-square constant, these constants are replaced by this function, because in place of constant unit vectors are changing with space. Those are reflected here, f1, f2, f3.
So our metric tensor is a function of position and time.
Yes.
Okay.
If you want to use the technical word metric